Welcome to The Explainer. Today we're diving into a genuinely fascinating new arXiv paper by researcher Mariam Zakaria Musa Ali. It introduces something called FraudShield AI. Basically, this is a hybrid model specifically built to shut down modern money laundering and financial fraud. If you've ever wondered exactly how financial institutions are trying to keep pace with today's incredibly sophisticated criminals, well, this is the architecture you really need to understand. Let's get right into it.
Okay, to start off, let's look at this absolutely extreme number, 0.13%. In the evaluation environment the researchers used for this paper, the actual fraud rate is a minuscule 0.13%. I mean, think about that for a second. Normally, when you're training a machine learning model, you want a pretty healthy, balanced mix of examples, right? But out there in the real world of financial transactions, the data imbalance is just off the charts.
And honestly, this perfectly illustrates why your standard AI fails so often in the financial sector. Trying to pinpoint that tiny 0.13% sliver of fraud hidden inside 99.87% completely legitimate everyday transactions, it's literally like trying to find a needle in a massive financial haystack. If a traditional system just lazily guesses that every single transaction is legit, it's still going to be 99.87% accurate. But obviously that completely defeats the whole purpose of having a fraud detection system in the first place.
So to understand exactly how FraudShield AI tackles this monumental needle-in-a-haystack problem, here's our roadmap. First, the financial fraud problem. Second, enter FraudShield AI. Third, merging graphs and LSTMs. Fourth, fixing extreme data imbalance. And finally, a reality check for developers.
Let's jump right into Section 1, the financial fraud problem, or really, the adversarial arms race.
The hard truth is, fraudsters just aren't moving millions of dollars all at once anymore. They know exactly where the bank's tripwires are. Instead, they rely on advanced evasion tactics, like layering and something called smurfing. Smurfing is when criminals take massive sums of illicit money and break it down into tiny, seemingly harmless microtransactions. Because traditional bank filters usually rely on these static, hard-coded thresholds, like automatically flagging any transfer over 10 grand, these little microtransactions slip right past the system, totally unnoticed. It's just a constant, exhausting cat-and-mouse game.
Which brings us to Section 2, enter FraudShield AI, and what is essentially a paradigm shift in detection.
The crucial takeaway here is the shift in perspective. The old way of doing things, traditional systems look at isolated transactions, one sender, one receiver, $1 amount, and then they apply those static rules. But real financial networks have incredibly complex topological properties that those basic static models just completely miss. FraudShield AI introduces a hybrid LSTM-Graph framework that looks at the whole board using network-level forensics. So instead of just asking, hey, is this one single transfer suspicious, the system models financial flows as a massive directed graph. It wants to see the broader relational context. It wants to see the whole puzzle.
All right, moving to Section 3, merging graphs and LSTMs to capture space and time.
To actually pull off this network-level view, the researchers handcrafted some very specific network-centric features. First up is PageRank centrality. You probably know PageRank from how Google ranks websites, right? But here, it's used to identify high-value routing nodes. Basically, it finds the central hubs in a money laundering ring. Second, they monitor in-degree dynamics, which is a fancy way of saying they track sudden, weird spikes in incoming transaction volume. And third, they use a custom flow ratio to quantify the actual directional movement of the money. Together, these three structural metrics brilliantly capture the spatial relationships of who is sending money to whom across the entire network. But look, space is only half the battle. You absolutely need time, too. Once those graph features we just talked about are extracted, they're fed into a long short-term memory, or LSTM network. The LSTM processes the temporal sequences, the timing, of these structural metrics. So by combining the graph's wide spatial view with the LSTM's memory of sequence and timing, the model can actually spot the temporal anomalies that happen right before or during sneaky evasion tactics like smurfing. And the paper even includes an ablation study confirming this. Both the temporal and the topological components independently boost detection accuracy. To win this game, you really need both.
Section 4, fixing extreme data imbalance. This is where we get to the secret sauce.
Let's get into the mathematical heavy lifting for a second, because having great graph features still doesn't fix that crazy 0.13% data imbalance we talked about at the start. To solve this, the researchers used a really clever trick. Standard AI uses an objective function called cross-entropy loss, which, again, just gets totally overwhelmed by the 99.87% of boring legitimate transactions.
FraudShield AI swaps that out for something called focal loss. Focal loss scales the cross-entropy term, intentionally shrinking the loss contribution from those easy, well-classified majority samples. In plain English, it forces the model's optimizer to ignore the obvious everyday stuff and obsessively focus on finding those hard-to-detect, super rare fraud cases.
And when you pair focal loss with their dynamic thresholding mechanism, it's a game changer. Remember those static, hard-coded bank limits that fraudsters easily dodge? FraudShield AI completely throws those out. Instead, it continuously monitors real-time transaction velocity. It analyzes the current network density, and then it dynamically adjusts the probability cutoff on the fly. So if the network suddenly gets hit with a flurry of rapid, dense microtransactions, which is the classic hallmark of a smurfing attack, the system immediately tightens its net to catch those low-value, distributed attacks that would normally just breeze right through.
And honestly, the results speak for themselves. When put to the test, this hybrid model substantially outperforms standard baselines like logistic regression and XGBoost across the board. We're talking higher precision, higher recall, and better F1 scores. According to the paper, the most massive gains actually happen specifically in those microtransaction fraud patterns that usually beat standard threshold filters. It's a really big leap forward.
But before we get too carried away, Section 5, a reality check for developers on implementing this in production.
Look, before you try to drop this into your fintech startup's code base tomorrow morning, you need to know this isn't just a simple plug-and-play SDK. There are some very real engineering hurdles here. First off, feature engineering for this is highly manual. Calculating page rank and flow ratio means constructing graphs and periodically recomputing them, which is going to add serious latency to your live pipelines unless you build out incremental graph updates. Second, that focal loss we were just praising, it requires incredibly careful tuning. You're going to be running grid search or Bayesian optimization to find the exact right balancing factors for your specific data, or it just won't work. And third, trying to deploy LSTMs right alongside CPU-bound graph algorithms can bottleneck your GPUs pretty severely if you don't aggressively parallelize the pipeline or use specialized libraries like PyTorch Geometric.
We also have to keep the evaluation scope in perspective. The paper tests FraudShield AI on PaySim, which, while widely used, is ultimately a synthetic dataset for mobile money transactions. It doesn't capture the messy, full complexity of a massive live production network. For real-world bulletproof adversarial resilience, this architecture absolutely needs to be stress-tested against live transaction streams where human attackers are actively adapting to the model's feedback loops.
So the big takeaway here for data scientists and engineers is to treat this arXiv paper as a brilliant architectural blueprint, not a finished, out-of-the-box product. It hands you the exact right formula, combining spatial graph features with temporal LSTMs and focal loss, but you're the one who still has to pour the concrete and build the infrastructure to actually run it in real time. Which leaves us with this final thought. Knowing the sheer computational heavy lifting required to continually update network graphs and run LSTMs with sub-second latency, you've really got to ask yourself, is your current data pipeline actually capable of shifting from simple, isolated rule checks to true network-level forensics? FraudShield AI proves that the math absolutely works and that the bad guys can be caught. But taking that next step, that's entirely up to the engineers. Thanks so much for joining me on this explainer, and I'll catch you on the next one.